Dimmi quando.
Partita.
Okay, so good morning, everybody. Today we will have the first part of the day, so morning and 2 hours of the afternoon. The two gentlemen here, Professor Lorenzo Brualla from University of Essen in Germany, and Colonel Carlos Ardanaz from the Spanish Army. And they will accompany you in a journey done about triage algorithms, Monte Carlo, and then with Cornell, that is the first part of Professor Brual, and then the second part with Cornell Ardanaz. He will show you a lot of case studies and lesson learned on CBRNE operation. So I leave the floor to Lorenzo, who is the first to start, and I wish you a nice day. Lorenzo, Carlos, thank you for coming here. You have the floor.
Thank you, Andrea. I'm very much pleased to be here, and thanks to Professor Malizia for this opportunity. He has told me about the heterogeneity of this group, which is really an asset, particularly in the view of the subject that we will cover today. As you see from the title, triage algorithms in mass casualty events, Monte Carlo simulation. I have collapsed the two talks of the first and second hour in the morning into a single title. And as you can see, we have triage algorithms. So this is something that we need to go through. Mass casualty events, that is also something that we need to study. And finally, Monte Carlo simulation. So apparently things that are very much dissimilar, we will put them all together. This lecture falls within a broader field, which is called theoretical medicine. And there is not much work in theoretical medicine. You know, in medicine, most of the research is done through experiment. And here we are doing something completely different. So we will go, first of all, through mass casualty events, then introduce triage algorithms, and finally, we will go into Monte Carlo simulation applied to triage algorithms in mass casualty. If you want to interrupt me, if you have questions, just stop me. I don't want to lose you through the whole process of the lecture, so that there are some parts you will see because of the heterogeneity of the group. Some parts for some of you will be very easy and you already know, other parts don't. And the idea is that at the end, we all come up with conclusions, and you also can contribute with your comments to this work, which is actually ongoing research. All the work that I'm going to present has been just published, as you see, 6th of May, so a few days ago. This is most of the work of my PhD student, Tobias Schwertfeger, at the Faculty of Medicine. So, first of all, what is a mass casualty event? Mass casualty events are situations in which the need for medical care exceeds the available medical resources. In general, it is defined as when you have more victims than medical personnel. In that situation where you cannot give immediate care to each single victim, then you have a mass casualty event. They are infrequent, but potentially overwhelming for the medical system. The fact that they are infrequent is good, in the sense that there are not so many mass casualty events, but it's bad in terms of the study of mass casualty events, because you do not have enough statistics and you do not have enough opportunities to study them. Therefore, they require an effective distribution of the medical care, leading to the challenging decision of which patients should be treated first. And here is when it comes the triage algorithms. And the decision of who must receive medical care first is a decision that must be taken usually in a chaotic situation and under time pressure. However, so the way we decide how we are going to, who we are going to treat first is what is the so-called triage algorithms. How do we take this medically challenging decision of who to treat first? Triage was introduced in the 19th century by a military medical doctor in war, and he had the idea of who how to classify soldiers that were injured in combat in order who to treat first. That is why it's called triage. It uses the French word triage, okay, which means to select. Okay. However, although triage is used repeatedly by most of first responder institutions throughout the world, there is a lack of support in terms of quantitative evidence of which triage algorithm, which triage procedure performs best. And we can see that in this review published by Lee Jenkins and co-workers. And just from the very abstract, they say, and I'm going to read that for you, evidence to support the use of one triage algorithm over another is limited. And the development of effective triage protocols is an important research priority. The most widely recognized mass casualty triage algorithms in use today are not evidence-based. And no studies directly address these issues in the mass casualty setting. Furthermore, no studies have evaluated existing mass casualty triage algorithms regarding ease of use, reliability, and validity when biological, chemical, or radiological agents are introduced. Concurrently, the lack of a standardized mass casualty triage system that is well validated, reliable, and uniformly accepted remains an important gap. So in summary, we know nothing. It is generally, and this is not the only paper that talks about these problems, that put the finger on the issue. There are many others. Decisions on which triage algorithm is adopted by each country or region are taken based on political aspects, tradition, and so on and so forth, but not on quantitative evidence. The reason is because there is no quantitative evidence of which triage algorithm works best. Why? First, there are no sufficient mass casualty events. And second, when there is a mass casualty event, no one collects data to conduct studies afterwards, or in most cases, data is not collected. So, what are we doing? What we are going to do is to address this problem. We are going to create a method to quantitatively evaluate mass triage algorithms in mass casualty events. We're going to look at mass casualty events that involve vehicles, car crashes, bus crashes, lots of victims from car accidents, burnt victims, either from chemical burns or heat, terrorist attacks due to shooting, drowning victims from ships, and human stampedes. So a wide variety of events. Many of them are closely related to nuclear and chemical weapons. As you very well know, in the case of nuclear detonations or in the case of terrorist nuclear attacks, most of the victims are not from radiological exposure, but are due to traumas, injuries because of the shock wave or human stampedes, people running in panic. These are most of the victims that would occur in case of a nuclear detonation, not because of radiation. And also those who are closer to the detonation because of bullets. So, how triage works? Triage is performed by the first medical team arriving to the scene. That means that the first medical team arriving to the scene goes to each victim, and the only thing that they can do to the victim in case the victim has the airway blocked is to unblock the airway. Apart from that, what they do is to evaluate the victim in order to decide to which triage category the victim will be assigned. And to do so, they use the triage algorithm that is enforced by their local authority. In general, there are 3 to 4 triage categories. Green, which are those that do not need immediate care. Yellow, which are those that need care in an expedited way. Red, that need care in less than 30 minutes. And in some triage algorithms, there is the black category, which means dead. In the case of Germany, the triage algorithm used in Germany does not have the possibility of the black card, dead, because triage is usually applied by paramedics. And in Germany, in order to certify death, it has to be done by a physician. Okay, that's the reason why there is not the black card in the algorithm used in Germany and in other countries. There is a 5th card that we are going to talk about, which is the blue card. The blue card is a card that, as far as I know, it's not used in any triage algorithm, but it has been discussed for some time, which is the expectant category. And this is the category for those victims that, although they are alive, their probability of survival is so low that it does not merit the effort to invest medical resources into them. And it's better to let them die, essentially. Okay? This blue card is not applied because of ethical concerns. Okay? But these ethical concerns have never been discussed in terms of quantitative evidence. And this is something that we are going to try to address. Finally, in general, the triage procedure has to be applied in less than 30 seconds per victim. So the paramedic has to take the decision of which card to deliver in less than 30 seconds. So triage algorithms must be designed in order to expedite. Okay, so we are going to analyze the following triage algorithms. MSTART, which is an algorithm widely used in the US. CurveLight, this algorithm has its origins in Australia. And it was designed for transporting victims with airplanes or helicopters, because distances in Australia are very big and it is highly unpopulated. Prior, which is the German algorithm for triage. We are going to propose an algorithm that does not exist, which is start blue, which is M start with the possibility of the blue card, and FTS, which is a military triage algorithm, which is designed for classification of victims, which are troops in the forefront. So this algorithm is addressed essentially to young male in combat operations, a young healthy male in combat operations. So let's have a look on how these algorithms work. They are very much similar, as you will realize. So M-star, the first question, is the victim able to walk? If yes, it's a green. I don't care if the guy lost 3 fingers. Is he able to walk? Yes, he's green, period. Okay. Next question, is the victim breathing after removing an eventual block of the airway? No, the victim is dead. If the victim is not able to walk but is breathing, then we ask about the respiratory rate between certain thresholds, which if the thresholds are not satisfied becomes red. If the thresholds of the respiratory rate are satisfied, we wonder whether the victim has a palpable pulse. If the victim does not have a palpable pulse, becomes red. And if it has a palpable pulse and the respiratory rate is within normal parameters, then we wonder if the victim can follow simple commands. And if the victim cannot follow simple commands, becomes red. And if it can follow simple commands, then becomes yellow, the intermediate category. Okay, so this is the algorithm. We're going also to study an algorithm called Jumpstart. Jumpstart is a slight modification of MStart applied to children, because the respiratory rate of children is slightly different from okay, but it's essentially the same. What about curve flight? We always start with the same question. Is the patient able to walk? Yes, then it's red. And then we wonder about the possibility of following simple commands, breathing after opening an airway, and the presence of palpable pulse. Okay, so look that in curve flight, there are no specific parameters for the pulse rate and the breath rate, just the presence of pulse and the possibility to breathe. That's it. And based on that, we decide whether it's green, black, red, or yellow. Prior, the German one, no black. And here we wonder, first of all, is there any critical bleeding? You see, this is a new question. This question did not appear in MStart or curve flight. If yes, it's red. Then we wonder about unconsciousness. If yes, it's red. We wonder about abnormal respiratory rate. If yes, it's red. Palpable pulse, yes, the lack of palpable pulse is red. And then we wonder about the possibility to follow simple commands, and if it is not possible to follow simple commands, then becomes red. If all these questions are no, 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 and the victim cannot walk, then it's intermediate. If the victim can't walk, then it's red. And finally, let's see FTS, the military one. The military one works based on you get 1 point if you have no pulse, and you get another point if you are not able to give response to simple commands. 0 points means that you are green, 1 point means that you are yellow, and 2 points means that you are red. So it's very, very simple. That's the idea. I mean, it's to be applied very quickly in the front line.
This is the case that no pulse and no response has the same
Yeah, the same level.
level. Yeah.
Yes. Well, if you have no pulse, you get 1 point. If you have
Because
no
if you have
response,
pulse and no response, and if you have response and no pulse,
in both cases, you are
here.
As you will see, I mean, I'm going to do a spoiler for you. It is very difficult to be a red victim with FTS, okay? So the number of red victims in FTS is much, much smaller respect to the number of red victims with any other algorithm. The idea is that you don't want to expose your medical resources to the front line to save a lot of people, okay? There are other triage algorithms that are somewhat studied within what we are presenting today. ASAF is a minor variation of MSTAR that considers hemorrhage, okay? It's using in the US. Then there is something called START, not MSTAR, but the START. And another one called triage-CIF. Both are very similar to MSTART, but they use capillary refill time. You know, when you press the finger and it becomes blue, and then you wait for the time that goes from blue to the normal color, which is closely related to the heart rate and the presence of palpable pulse. However, the problem with the capillary refill time is that, first of all, you need to apply it in situations where you have good illumination, which is not always the case in mass casualty events. You can be in darkness, you can be surrounded by smoke, so it's difficult to evaluate. And second, there are no publications that relate capillary refill time with a heart rate directly, that give you an equivalence, which is not the case for the palpable pulse. The pulse rate, you can have a relationship, so you can quantify that much easily for the of computer simulation. SALT, that's another algorithm applied in the US, which relies on answers given to non-quantitative and ill-defined questions, such as the presence of minor injuries, which is difficult to define what is a minor injury. So there is not a clear list of what is a minor injury, or beyond which size of the wound and which place is a minor injury or not. So it's quite subjective. And also about the SALT has questions about the likelihood to survive, which is also a subjective question and therefore ill-defined, not adequate for program. Finally, Jumpstart, that I already mentioned, which is a variation of MSTART, in which the respiratory rate thresholds have been adapted to children, and which we are going to study. Okay, so far so good? Yep. Questions? Now we are going to jump into another subject. Okay. Let's go into another subject, and then we make a short pause. Now we are going to go into something completely different. So stay with me, and then we will put everything together. The Monte Carlo method. Okay. Raise your hand who has ever listened to talk about the Monte Carlo method. Okay, listen, I mean, just listen to that you know that there is something called Monte Carlo method, whatever it is. Okay, good. So the Monte Carlo method is a mathematical method for solving problems in which essentially you do not know much. Okay. Said in more precise words, you are going to solve integrals that you do not know how to solve. Okay. And this method was conceived during the Manhattan Project in Los Alamos when they were doing the atomic bomb. The idea, the problem that they had was to study the path of the thermal neutrons acting as moderators in the process of enriching uranium. The Monte Carlo method uses random numbers to do calculations, and that's why it is called Monte Carlo. The guy who invented it, Ulam, a Polish researcher at Los Alamos, had an uncle that was millionaire and lost his fortune in Monte Carlo. So he was all the time talking about his uncle that lost all the money in the casino of Monte Carlo. And then they came up with the name of Monte Carlo because they were using random numbers. Okay. So to show you a very, let's say, the academic problem that everyone shows when explaining Monte Carlo, I will show you the problem of computing the value of pi, okay, using Monte Carlo. So let us assume that we have a circle of radius equal to 1, okay? And we circumscribe this circle within a square. Therefore, the size of the square is 2, and as you very well know, the area of that square is 4, okay? Here. Therefore, 1/4 of the area of the square is 1, right? So far, yeah, that's easy. Okay. Why am I taking 1/4 of the area? Okay, I am doing so because I see that in this figure, I have a fourfold symmetry. So if I just care about one of the quarter of the figure, and I solve the problem for 1/4 of the figure, then it is automatically solved for the other 3/4. Okay, and doing it in that way, knowing that there is a symmetry, I can solve the problem quicker, and you will see why I say quicker in a minute. So how much is the area of the circle? The area of the circle is pi times r squared. R equals 1, so the area of the circle is pi. Therefore, 1/4 of the area of the circle, that is this region here, is pi divided by 4. Yeah. So far, so good? Okay. And now it's when the magic comes. The area of the circle divided by the area of the square is proportional to, if I start to drop in this whole area, points at random, some points will fall within the circle, some points will fall outside the circle and within the square. If I divide the number of points that fall within the circle by the total number of points, this quotient is proportional to the areas of the circle divided by the area of the square. Okay, and you will see that in a moment. And from this equation here, you can isolate pi and get that pi is 4 times the number of points that went into the circle divided by the number of points that went into the square. You will see this in action. And here you have the value. You see how the value of pi is improving as I drop more and more and more. Okay. Eventually, if I drop an infinite amount of points, I would have an exact value of pi. So first of all, Monte Carlo is an exact method. It provides you an exact solution, but it provides you an exact solution with infinite amount of time. Okay. Therefore, what you need to give with all Monte Carlo results is a statistical uncertainty associated to the value that you are giving. Okay. And there is a way to compute the statistical uncertainty, and we will not go into that in detail. But you see, here, this is the number of points that have been sampled. So for 10,000 points, you will see at the end a value of 3.15. So you are only on the first decimal place after 10,000 points. And this goes into the next issue, which is the main drawback of Monte Carlo. The uncertainty is reduced as the square root of the number of points or the number of histories of samples you are doing. So if you want to reduce your uncertainty by a factor of 2, you need to multiply your simulation time by a factor of 4. And this is the main drawback of Monte Carlo. Yes, please.
Yeah, the question is for the points in the square.
Yeah.
I thought that the points in the square are the total points released in the illustration. But this illustration shows that
Different color.
the points is only out of the square, out of the circle, and in the square.
You can do it both ways, but you see here, this N, R is the number of points in red, P is the number of points that are in the square, I mean, in the region that is a square but not circle.
Okay.
But then what they use is N, which is R plus B, which is the total number of points. I was referring in the previous slide to N, the total number of points. Okay.
So in the formula, you don't use n as the total number of points.
You use N, and this N here is the 10,000.
That is the total number.
Is the total number of points. So that's why, imagine that you cover the figure with points everywhere, very tight together. So the quotient between the number of points here in the circle and the total of number of points here is the same as the quotient of this area divided by this area. Doubts, questions? No? So this is the essence of the Monte Carlo method. I mean, the Monte Carlo method is used almost for everything, essentially. You can use it for simulation of radiation transport in material media. You can use it for solving quantum mechanics problems. You can use it to study the stock exchange values in the market. People use Monte Carlo method essentially for ends. Okay, and yeah, but the essence is always the same. You create random samples and then you study these random samples. So what we are doing here, we are randomly dropping points in the area, and through that we get the value. Okay, so let's stop for 5 minutes. Let's meet again at 9:45. Okay, and then we go.
Ahora lo entendí. Ahora sí. Lo bueno es que he recordado una lección de bachiller, que me acuerdo de un compañero dijo en clase, pero profesor, ¿qué es una integral? ¿Qué es una integral? ¿Qué hace una integral? Y nosotros le dijo, una integral es la suma de términos infinitesimales.
Y ahí se quedó tan claro, no entendí nada.
Sí, sí, yo me quedé con eso y, claro, entendí para qué servía la integral. Y está aquí me
Sí, sí, ahora estamos en golpe. Ahí todos en Estados Unidos.
Che probabilità c'è? Sono io. Non so, da 45 anni.
Hanno il metodo della scimmia. E l'idea è che la scimmia
La verdad es partido de es que no era esa vez, luego americano que se olvidan del final de la palabra. ¿De qué está hablando? Y luego te mira y dice, ¿de qué idioma hablas tú? Digo, estudio pescoya.
una gente, tú no lo has entendido. Mentalmente.
Y ahora espera a ver qué es lo que me viene después. Ok. Ya viene la parte de cómo aplicamos el Monte Carlo para combinar todo.
Pues yo luego, la parte mía de triar, presenta unas cuantas cartas de viaje que están recomendadas por la Agencia Federal de Aplicación. Que deben ser
Start, sí, ellos son Start o Start es Modified Start.
Es que no menciona el modelo de trias en lo que yo tengo en la publicación.
O sea, el algoritmo que sí que se
Era ese. Porque además usa colores más el negro también.
claro. Pero los americanos sí que cualquiera puede, un policía puede certificar la muerte.
Pero en ese caso, para la de no lo digo de esto, el negro lo ponen como expectant.
Ah, sí.
Sí, sí, lo he explicado.
O sea, el negro es el azul.
Sí, y dicen, cuando tú ves que tiene un tío trauma y heridas, quemaduras, negación aceptado por la redacción, sabrás que todo no vaya a ningún lado. Entonces, la política negra, expectan, y en eso parece que no falla aquí. Ganamos frío, ahí se queda marcado.
¿Tú sabes ahí? Que los americanos que
Caramelo, ¿no?
no sé cómo, sí. Sí, viene pastillas, pero te quita el síndrome de irradiación inmediatamente. Así también. Sí, sí, es que eso te lo digo. O sea, para los también puestos que tienen 48 horas que se las pasan vomitando es tómate la pastilla, te sientes de puta madre y estas 48 horas puedes seguir combatiendo. Y además, tranquilo, porque sabes que no tienes nada que perder, eres investigador. Entonces, es el que ahora le da a mi paciente de radioterapia y a un paciente de o sea, hace 15 o 20 años en el hospital público se estaba yendo el momento de ahora no hay donde en ningún sitio. Perdón, tengo que venir. A mí, el médico con el que yo trabajaba, que era mi jefe, del barco te desvía, te da un mareo chulo y me dio una caja de yo me cago un poco y tal. Digo, coño, yo no me atrevo a tomar esto. No pasa nada.
Efectos secundarios,
¡Tómate!
que no te va a hacer alguien en el barco.
No. El tío es un berserk, una cosa así. ¡Tómate! Vale. Ya les he dado 6, me faltaba uno para. O sea, eran menos 6 de la hora.
Ahora se empieza. Yo voy a 45, empezamos a 45 y
El que se queda.
ya, porque estoy viendo que están entrando.
Ahora tengo 1 hora y 1/4 por delante. Platicamos bien.
Sí, pero mira, voy por la 14, pero menos 50.
Bueno, sí,
Dije por 3,45. O sea, que estás ahí en el tercio más o menos.
sí, sí.
Y en el tercio se enrolla mucho. Si ves, has presentado y es una audiencia.
Sì, però si permette di masterizzare se tu ragioni in termini di riduzione del rischio, la differenza è che del rischio sulla crisi.
Estas son 5 que faltaban para el blancas del mérito militar. Esa por las Pues es la de Afganistán, no me acuerdo cuál es. Está en Líbano, una es Kosovo, Macedonia y Afganistán. Esa no la he esperado. Yo me fui a Afganistán en el 2008 con los paracaidistas. Ya muchos años, y se a destruir y venía a ya me sé toda esta gente que van a ir a Afganistán. Y de casualidad, un colega había una plaza libre de contingente de paracaidistas con necesidad de cargar de militares. Y me fui para allá con un par de videojuegos para escanear y pues inicialmente combate, salía territorios que si entraba te iba a combate. Cada mes entraba una vez un maravilloso de museo. Cada mes, para comer. Sí, era una operación contra inteligencia. No es como Ucrania, que es combate de trinchera y artillería, emboscadas, negociación, la parte de negociación, la parte de civil. Las autoridades del gobierno de la República Islámica de Afganistán, con comando civil y son tribales. Hay tres poderes. Ahí estaban las tribus, los barbudos que eran llamados los religiosos, y luego el gobierno. Eran tres poderes ahí. Y dicen que realmente es un caso que uno de los tres tribales que es difícil. Como he dicho cuando encontrar el tribal. Así ese país está ahí complicado. Entonces, contigo un whisky.
Este es en el barco, ahí con...
Sí, en el barco. Y la medalla yo no la espero. De hecho, se me hizo nuevo 2 cruces rojas, que son las de las de promoción y al capitán que mandaba la compañía de tripulación, pues la ganaron. Y yo estuve en esa misión, de casualidad. Y cuando todo esto hubo un aumento de crédito disponible para poner cruces blancas. Y sin ser paracaidista, que es lo más. Me pusieron para una ruta. Ellos, que siempre prevalecen a los suyos. En vez de yo le noté por cada con el de defensa.
O sea, te enteraste.
Me enteré por el día.
O sea, eso no es que te la
Me la pone un acto después de la publicación. Y yo me enteré por la publicación. Se llama a agradecerle un paracaidista de estos.
los paracas con los
Con la edad, Te das cuenta que son gilipollas. No eres teniente. Pues ahí, luego ya de mira, yo salgo todos los años en Afganistán, en Irak y eso tampoco es como tener a otro estilo, el estilo es diferente. Venga, vamos a empezar.
Niño, sí. Okay.
Let's start. Please take a seat. Okay, so okay, so let's continue. Now let's put together the Monte Carlo method with the triage algorithm, okay? With the idea to compute quantitative estimations of values that will allow us to evaluate the triage algorithms, okay? So to do so, we will create two programs, okay? The first program is the actual Monte Carlo program, in which we are going to create virtual casualties. Virtual casualties. So these are, each of these virtual casualties is like one of the dots in the circle that we just saw, okay? And these virtual casualties will, as the connectivity of these virtual casualties will represent the victims of an actual mass casualty event. We will create virtual casualties for one of each of the type of mass casualty events that we saw at the beginning. The vehicle, the burning, the sinking ship, the stampede, and the missing one. Ship. Stampede and the shooting, sorry. Yeah. And the terrorist attack. Okay. So for each type of event, we will create virtual casualties. How many virtual casualties are we going to create for each type of event? We are going to create 600,000 casualties. So our mass casualty event of the crash will be a very big crash with 600,000 casualties. Our sinking ship will have also 600,000 persons drowning in the sinking ship, and so on. Why these large numbers? Because we want to reduce uncertainty. We need to do statistics. Okay. And then it comes the key question. How are we going to create these virtual casualties? How do we know that these for example, these 600,000 victims of the car accident are representative of the actual victims of car accidents? To that end, we are going to use the American National Trauma Data Bank. There are only two countries that keep a public registry of victims of individual accidents. I am not talking now about mass casualty events, I am talking about individual accidents. One is the US, the other is Australia, okay? And both countries allow you to get that information. You need to pay a small amount and they send you the data for all the casualties for a given year. So we bought all the casualties, the data, the medical records of all casualties that occurred from individual accidents in the United States during year 2016. Okay.
What type of accident? Car accident?
Not all victims of all type of accidents. So that database contains all victims from every type of accident.
Work-related car explosion.
Accidents. Yeah, it's really amazing. They have you pay 500 euros per year, which is extremely cheap, and you get all except for the name. It's anonymized. You have all the information. What information do you have? For each victim, you have, of course, the type of accident. You have obvious information such as the age and so on, but you also have information about the injuries, the medical procedures that were applied, the vital signs at the time of the accident, how was the discharge of the patient, whether survived or not, and you also have information about comorbidities. Okay. Comorbidities are diseases that the person has before the accident. For example, high blood pressure, okay? So the consequences of an injury on a person that has high blood pressure are not the same on someone who has not high blood pressure, okay? So you have all that information. It's each record of each casualty of each victim is very, very complete, okay? And you have all the type of injuries, you have all the type of medical procedures applied, everything is coded following the standard medical codes, okay? So we are going to create these virtual casualties using the information contained for the real victims of individual accidents in the National Trauma Data Bank, in particular for year 2006. Once we have these records of virtual casualties, and we know for everyone that the whole story of each virtual casualty, we are going to apply the different triage algorithms, okay? And we are going to compare the outcome of the triage algorithm, of a given triage algorithm for that casualty, red, yellow, green, whatever, with the ground truth. And now I will tell you how we are going to know the ground truth. But first of all, we need to define certain medical terms that we are going to use for the simulation. First of all, we are going to use the AICI, the Australian Injury Comorbidity Index. The AICI quantifies the effects of comorbidities. Remember what comorbidities are? Diseases that were before the occurrence of the accident. Okay, so quantifies the effects of comorbidities on accident victims. And there are 11 comorbidities associated with in-hospital death after trauma. Okay, this has been studied, and there are 11 comorbidities that are really important. The person gets, the virtual casualty gets 1 point per comorbidity that the victim has from this list of 11 comorbidities. So if one of our virtual casualties has an ACI value of 3, that means that this person has 3 of these 11 relevant comorbidities, okay? Then we are going also to use the AIS, the abbreviated injury scale. This one assigns an increased level of severity from 1 to 6 for each injury. And there are 114 coded injuries in the ICD-10. The ICD-10 is the list of all injuries, diseases that a person can have, okay? Every possible health abnormality is coded within the ICD-10, and within this very long list, there are 114 injuries. And the severity of each injury is quantified according to the AIS, okay? Then we're going to use the NIS, which is the new injury severity score, which is obtained by adding the square of the AIS for the 3 most severe injuries, okay? So we look at the 3 most severe injuries and we add the square. Let's say that someone has 3 injuries with a score of 5 each one. So is 5 squared is 25, 25 plus 25 plus 25. The NISS for that casualty would be 70. Okay? If any injury has a value of 6, which is the maximum AIS, then then the NIS is automatically assigned to 75. So the maximum value that NIS can take is 75. The minimum is 3, okay, because you need 3 injuries to get an NIS score. And if they are very light injuries, then you get 1 point per injury. 1 squared is 1, added 3 times is 3. Okay, clear? No questions? Okay. It's easy. Then the Glasgow Coma Scale, those with medical formation know very well what the Glasgow Coma Scale is. The Glasgow Coma Scale is a method to assess the consciousness of a patient. You get 1 to 4 points, with 4 the maximum for the possibility of opening the eyes. 1 to 5 for verbal response, so the person speaking perfectly has a 5, and 1 to 6 points for motor response, so the ability to move following simple commands. 6 is a person that is moving normal, and then you add all these points. The maximum that you can get 4 plus 5 plus 6 is 15. The minimum is 1 plus 1 plus 1, which is 3. So 15 is a person normal. We all here have 15. 3 is a person in deep coma. Okay. Blood pressure. Blood pressure is related to palpable pulse. There is a study which indicates that the probability of not detecting palpable pulse is 15% when the systolic blood pressure is less than 80 millimeters of mercury. Okay? So if you have a low blood pressure, there is a large probability that although you have pulse, it is not detected. And even if you have a normal systolic blood pressure that is higher, much higher than 80, there is still a 0.55% probability of not being detected. Okay? These probabilities are into the Monte Carlo simulation. Finally, the walking capacity. As you see, we are using the National Trauma Database for creating our virtual casualties. However, the National Trauma Database does not state whether the victim can walk or not. We need to infer that information from the National Trauma Database. And to do so, we see that there are essentially 2 transportation methods that are recorded in the data bank to arrive to the hospital. One is being transported by private car, walking in by the police. We assume that anyone that arrives by a car, by the police, and walking in is a person that can walk. The other possibility is to be transported by an ambulance, air ambulance, ground ambulance, whatever. If the person is transported by an ambulance, we do not know if the person can walk. So in that case, we wonder, is the Glasgow Coma Scale equal or greater than 13? Yes, then the person, so 13, 14, or 15, we assume that the person can walk. Less than 13, then we wonder about the knees. Remember the knees, which is the summation of the square of the three most severe injuries. And if the knees is greater than 10, we assume that the person cannot walk, okay? And these values have been, these thresholds have been derived from publications. So this is a way to infer whether the person can walk. And now let's go to the reference category. The reference category, which is the key issue for the whole method, because we are always comparing the outcome of whatever triage algorithm we are analyzing with the ground truth. The ground truth, we establish it through the knees. And this has been demonstrated that is a valid and accurate way of assessing the general health condition of a person. If the NIS is less than 16, this is a green. If the NIS value is between 16 and 25, it's a yellow. And if the NIS is greater than 25, it's a red. This is our ground truth. Okay? As you see, that in order to evaluate the NIS, you need to conduct a thorough medical exploration of the victim. That is the reason why the NIS cannot be used in field when you are in the triage operation. In the triage operation, you can do very quick things, detect palpable pulse, see the person can walk, if the person can respond to simple commands, and evaluate the breath rate, nothing else. The NIS requires a thorough medical examination, okay? And what happens? Remember that the NIS requires that you have at least 3 injuries. If the victim does not have 3 injuries, then we go to the AIS. And the AIS is the severity of each injury. We go to the most severe injury, and if the AIS is less than 3, it's a green. If it is 3, it's a yellow. If it is greater than 3, it's a red. Okay? And now we are going to explain how is the creation of the virtual casualties. Here is where we are going to use the random numbers, okay? With the computer, we can generate very easily, we can generate random numbers that are uniformly distributed between 0 and 1. Uniformly distributed means that you have the same probability of getting 0.1 than getting 0.2, than getting 0.33578, whatever. Okay, all numbers have the same probability of being selected in the interval between 0 and 1. But we do not want to sample uniform probability distributions. Therefore, we need to use something called the inverse transform method, which is essentially solving this equation, the sampling equation, in which the P of X is the probability distribution that we want to sample, and we want to sample this probability distribution with a uniformly distributed random number, okay? And we are going to get this chi through solving this equation for each of the parameters that we are going to study. Now we are going to see that in action, but before that, let's see how the algorithm works. First of all, the algorithm for creating the virtual casualties. Remember, there are 2 algorithms. One creates the virtual casualties, the other applies the triage algorithms on our list of virtual casualties. So first of all, we start the algorithm, we define the type of mass casualty event that we are going to study. Let's say, for the example, let's say that we are going to study car victims, victims from car or vehicle accidents. So what we do is we remove from the National Trauma Data Bank all victims that do not belong to a car accident, and we keep only those that belong to a car accident. And then we study, first of all, the age. So we see the histogram of the age, and we select randomly the age of our casualty, and then we remove from the trauma data bank all the remaining victims that do not have that age. And then we go to the next step. We study the ACI. Now we are studying the ACI only on those victims in the trauma database that suffered a car accident and that belong to the same age group than our victim. So the ACI, let's say that we choose an elder by chance, an elder victim. We are going to see diseases typical from elder people. High blood pressure, diabetes mellitus, for example. If we select for another casualty, a child, high blood pressure is not very likely. It could occur, but it's not quite likely to occur. We will have then the typical comorbidities from children. Okay? We select the ICI and then we remove all the victims. Let's say that we have randomly sampled a person with an ACI of 2. So all those who do not have an ACI of 2 are removed. And now we are focusing on only those who have an ACI of 2, and then we see which are their vital signs, and so on and so forth. Okay? So these are conditional probabilities. And at the end, we create the casualty, and once we have the casualty, we store it. And if we have not reached this number that we set at the beginning of 600,000 casualties, we create another casualty. Let's see it in action. This is the age, okay? This is these age groups are defined according to medical publications, like children, adolescents, adults, and elders. Let's say that following the inverse transform method, we selected this just for one of the victims, and then we go to the ACI. And now you see the ACI, most of the people in that age group do not have any comorbidity, 0 comorbidities. Some 30% have 1 comorbidity, 10% have 2 comorbidities, and then you have something like 3% who have 3 comorbidities. Okay. So we selected just by chance this one with 2. And then now we are only looking at those people in the trauma data bank that suffer car accidents, that are in the elder group, and that have 2 comorbidities. Well, in this group, which are the most common injuries? Crashing injury of the head, fracture of the head, dislocation, sprain, strain of joints and ligaments of thorax, and so on. All those have some meaning. Okay. Well, let's say that just by chance we chose the most probable one. So we know we can also choose several ones. So this also happens. You can have several injuries. Okay. And we follow the distribution of injuries of the trauma data bank. And then we go into the blood pressure. Okay. This is very curious, and this is relevant to discuss. The blood pressure, as you expected, is distributed as a Gaussian distributor, normally distributed. But you see that there is a background, and then you have these peaks that are also normally distributed. Why? Well, we are using experimental data from the National Trauma Data. It is unlikely that someone recording the blood pressure records something like 123. Okay, so the most likely value that we'll code is 125 or 120. That is why for the round numbers, you have more casualties. Okay, this is the problem of working with real life data. Okay. Nevertheless, this does not affect the result because, okay, this is more likely than this, but it's very similar. Okay, so it does not have a consequence. The same occurs with the pulse rate, the respiratory rate, and now here we have the Glasgow Coma Scale. Okay, so you see the most likely result is 15, which is a completely normal person. 14 is you have some small disorder, and 3, which is deep coma, you have a substantial number. Okay. Transportation mode. Here you have the possible transportation modes in the database: fixed wing ambulance, ground ambulance, helicopter ambulance, and then you have all these that we already mentioned: other, police, and walking. Okay, or private. And for each victim in the trauma data bank, we have at the end the outcome. The outcome is binary, it's death or survival. Let's say that our victim survived, and we select that just sampling random numbers. So here you have something like 98 probabilities of that the victim will survive, but there is still a 2% probability that the victim will die. Okay? But this probability is not the probability, remember, of the whole database, but it's a probability condition for someone that have been going through all this process, because we have been systematically removing all those that do not fit the previous condition in the process. And this is our virtual casualty. It's a virtual casualty that had a vehicle accident, is an elder with an ACI of 2, diabetes mellitus and a bleeding disorder, had a crushing injury of the head, blood pressure 120, pulse rate 84, respiratory rate 16, GCS 15, transportation mode ground ambulance, and survived. And then we repeat this process 600,000 times to create this long list of casualties. So what do we do now? Well, this is just to see the variables that are used in the study. These are the variables that are in the National Trauma Data Bank. Then we create a modified National Trauma Data Bank, modifying the comorbidities and so on. These are the variables that are related to the virtual casualty, and these are comments regarding whether the variables are continuous or discrete and so on. Okay, and then we apply the triage algorithm. Remember, we will be always comparing to the outcome of our triage algorithm, because we know for that casualty, we know the pulse rate, we know the heart rate, we know the walking capacity, but we also know the NIS and the AI. We know the AIS and we can derive the NIS. So we know the ground truth and we know the result of each triage algorithm applied to the casualty. We also know whether the victim survived or died. Okay. So the first thing that now we are entering into the comparison with the very few published data that exist. So the first thing that we can do is to compare the outcome of our simulation with the results from actual, real-life mass casualty deaths. In the case of the burning, our mortality rate is 6.6%. Okay, the mortality has nothing to do with the triage algorithm. It's just people who died. Okay. We compare with the Nanjing chemical plant explosion, 4.3%. So it's reasonably good. Shooting, our mortality rate 9.7%. The Kansas City nightclub shooting 11.8%, which is also reasonably acceptable. For the crashing of vehicles, our mortality rate is 3.1%. In the US, there were 1.2% of fatal victims in car accidents. Okay, we are, let's say, more or less there. The stampede, our simulation gives 3.5%. The Love Parade stampede disaster in Duisburg was 3.2%. And the ship is the most difficult one, because drowning victims, depend a lot on the type of medical care they receive. So, for instance, the motor vessel Jola in Africa, when it sank, the mortality rate was 96%. If we compare with Costa Concordia, you all remember 0.8% of mortality rate. We obtain 1.8%. So this is the most difficult to compare because it depends a lot on if you are taken out of the water or down, essentially.
Excuse me. Just to confirm, the mortality rate affairs casualties or any injured person, or the total, so Costa Concordia, they transported them.
Yeah, okay, the 0.8% is the number of dead people among everyone, crew plus passengers. If you compare the number of casualties in Costa Concordia, death victims, with the number of people who received medical care, they were 30%.
Okay.
Okay.
And so for Love Parade, for example,
This is the percentage of people who receive medical care.
Okay.
Yeah. Those who were, I mean, Love Parade, there were thousands of people.
Before 10,000.
The exact numbers were something like 20, 30 people who died in Love Parade. Okay, so remember at the beginning, we went through this abstract saying that there is almost no quantitative evidence of the validity of one triage algorithm over another. What I'm going to show you now is all the quantitative results that exist up until now. And then we have done a very, very thorough bibliographical research. So if you know of anything else, I would appreciate very much. First of all, there is a master thesis of Friedhof Brunel. He's from, he works for the Rettungshilfe in Germany, the first emergency agency. And he studied only the prior algorithm, which is the one applied in Germany. And this is the only study that contains data from actual mass casualty events. So although it includes only one algorithm, the data contained therein comes from actual mass casualty events. He studied bus accidents, burn accidents, and terrorist attacks. However, his terrorist attacks are slightly different from ours because his terrorist attacks included bombing and shooting, while ours only contain shooting. Okay. Then the publication from Hela and co-workers, they studied MSTART, prior, curve flight, and FTS. So the same algorithms that we are studying. In the same way than we do, they use individual accidents collectively grouped as a mass casualty event, okay? And they conducted a retrospective study on 500 single accident victims, okay? The ground truth is determined by subjective evaluation of medical records. Then we have the work of Gardner. They studied MSTART and curve flight. It's also a retrospective study of individual accidents. And the ground truth is established through the medical procedures that were applied during the first 6 hours after the accident. Most of the accidents are vehicle accidents. Then there's the work of Gooch et al. also only prior because it's a German group and they are interested only on prior. And this one is based on exercises. Okay, it's an exercise-based study with 132 patients. Okay, and they are focusing on explosion events. And the ground truth was determined in advance by the designers of the exercise. And Jerome et al., they only studied start, and it's a retrospective study using single accidents, and the ground truth is determined through the application of severe medical interventions such as chest tube or CPR. And there's nothing else. So our comparison with Brunner. Sorry. So remember, Brunner, the only guy that has published data from real mass casualty events. The bus, he classified 12% in the red category with an uncertainty of 16%, so 12 plus minus 16, very large uncertainty because he's using real life data, not so many people in the bus accident, okay? And we are in line with the central value, 15.7 plus minus 0.4. More or less the same. I mean, we get compatible, statistically compatible results for red, yellow, and green category. The same occurs with Bern. It has 3 plus minus 6%. Okay, so it's compatible with our result of 10.4 plus minus 3. This is just one standard deviation. Where there's a larger difference, which makes results not statistically compatible, is in the case of the terrorist attack. And we think it is because the fact that Brunner considered bombing victims and we did not. Okay. Over and under triage. That's very important because now, okay, we need to define which are the criteria that we are going to use to evaluate our triage algorithms. So first of all, we saw the mortality rate. Then, with the case of Brunner, we saw the percentage of victims in each category. Okay. Now we are going to talk about over and under triage. What is over and under triage? Over triage is when you classify, let's say, a victim that the ground truth is yellow, you classify that victim as red. This is over triage. In that case, it's very good for the victim because this victim will receive immediate medical care, but it's not good for the group because you are delivering medical resources to someone that does not really need or not with that urgency. Okay? Under triage is the other way around. Someone that should be, for instance, red is classified as yellow. And this is very bad for the victim because he's not receiving the adequate medical care on time. So there is a metric called the delta T. The delta T is how far are you in terms of triage categories from the ground truth. Okay, so if So if your delta T equals 0, it means that your ground truth coincides with your triage category. And here we have the study for the results for MSTART, prior, CareFlight, and FTS. And those that have the label EXP are the results from HELA. Okay, so this is the comparison of our work with HELA. As you see, here we have the yellow, which in our case is very close to the 0, and this is the yellow from HELA, and this dot is the difference between us and HELA. How far are we from the result of HELA? Okay, remember the results from HELA are experimental because they use real victims, but they consider individual accidents grouped together as a single mass casualty. Okay. As you can see in all cases, M-star, prior, curve flight, the yellow category is almost very well determined. The red category is not that bad. And where you have large discrepancies is in this case. However, something noticeable occurs for FTS. As we already said, FTS has very demanding criteria in order to become red. So many victims that should be classified as red, they are not. Okay, because of, but this should not be taken as an error of the triage algorithm. It is just by design. This is what you want. This is how you want FTS to go. Another metric that we want to study, sensitivity and specificity. Okay. Only you are well acquainted with what sensitivity and specificity is. Nevertheless, let's go very quickly. In order to define sensitivity and specificity, we need to know what is true positive. True positive is sick people correctly identified as sick. A false positive, healthy people incorrectly identified as sick. Then we have a true negative, which is healthy people correctly identified as healthy. And we have a false negative, which is sick people incorrectly identified as healthy. And with these four definitions, we can define sensitivity, which is the number of true positives, that is sick people correctly identified as sick, divided by the total number of sick people. And the specificity is the number of true negatives, that is healthy people correctly identified as healthy, divided by the total number of healthy people. Okay? The combination of sensitivity and specificity, actually 1 minus specificity, you see from here, you can see that sensitivity and specificity are two quantities that go from 0 to 1, okay? So if we plot in the ordinate axis the sensitivity and in the abscissas the value of 1 minus specificity, we get this kind of plot. The diagonal corresponds then for each algorithm and each type of event, we draw a point here, which is we obtain the sensitivity, we obtain the specificity, then we compute 1 minus the specificity, and we get a point somewhere in this area, in this triangle, okay? If a point falls in the diagonal, that means that this algorithm is not capable of telling you anything, okay? This occurs when the sensitivity equals 1 minus the specificity. You cannot distinguish a sick from a non-sick person. The best point you can be, the best an algorithm can perform is when the sensitivity is 1 and the 1 minus the specificity is 0, because 1 minus the specificity is 0 means that the specificity is also 1, and then you are here. This is the objective. We want to be here. A perfect algorithm would be here. And now you see this cloud of points. This cloud of points is the evaluation of all triage algorithms for all the type of events, of mass casualty events that we are considering. And you see that they are quite far, except for this case that are somewhat close to the sweet spot. They are quite far from the sweet spot. Here, we also have not only our results, but we also have the results from Hella and from Gam. And we are quite close also to that. I will not go into detail of which point is what. You have that here. That will take us hours. But the general message is that triage algorithms perform far from. This radial plot here, this is a spider plot here. What shows is the distance of each point for the stampede, the ship, the shooting, the burn, the vehicle, and the average of all mass casualty events, the distance to this point here. So the closer you are to the center, the better the mass casualty event, the triage algorithm performs. Okay, and continuous lines correspond to the evaluation of sensitivity and specificity only for critical victims. Okay, those who are red, because essentially this is what your algorithm performs very nicely for green people. That's good, but that's not really what you want. You want to be able to tell those who are really red from those who are not. Okay, those that really require medical attention. So the continuous line corresponds to the results of only focusing on red victims, and dashed lines correspond to the total of victims. If you take into account of the total, you see that the dashed lines in general, they are within the circle determined by the continuous line. The quality of all triage algorithms gets lower with increasing level of severity of the victims. And that is common to all triage algorithms. Okay. So, now we are going to start to see which kind of nice things you can do when you have a tool like this. First of all, we can wonder about the influence of paramedic uncertainties on the quality of the results produced by the triage algorithm. So typically, the paramedic does not wait 1 minute to evaluate the respiratory rate. Remember that the paramedic has 30 seconds for the whole evaluation. So the normal procedure is to evaluate the respiratory rate during 15 seconds and multiply by a factor of 4. This has been studied, this procedure has been studied, and it has been found that this introduces a standard deviation of 15% on the respiratory rate band. We introduce this 15% uncertainty in the evaluation of the respiratory rate by the paramedic in the simulation. Regarding the palpable pulse, 6.9% of paramedics fail to detect palpable pulse in less than 5 seconds, which is the maximum time allowed for the detection of palpable pulse. Okay, we also introduce this into the simulation. And regarding the Glasgow Coma Scale, there is a maximum. Remember, it goes from 3 to 15. The Glasgow Coma Scale, 15 is a normal conscious person. There is a maximum deviation of 5 points from, let's say, a value established by knowledgeable medical doctors. And this, the distribution of this maximum of 5 plus minus points is follows a distribution published by Holgate. Okay? So, of course, it is more likely to make a mistake in the GCS of 1 point and of 2 points and of 3 points, okay? But it can be up to 5 points. A deviation of 5 points is very unlikely, but it could occur. So introducing all these uncertainties, we define what is called the nominal parametric, okay? In contrast with the perfect parametric. The perfect parametric in the simulation measures the vital signs that are recorded for each virtual casualty. So if the virtual casualty has a pulse rate of 120, you get 120 periods, okay? However, the nominal parametric, the result that gives is conditioned by these typical uncertainties. And as you see, so perfect in the vehicle, burn, shooting, ship, stampede. And here you have all the casualties, all the algorithms for the casualties that are critical in red, and casualties that are intermediate, yellow, the same, all the algorithms. And what you see is that the values are essentially the same. Some cases you have a little, very small difference, which is compatible within the statistical uncertainty of the results. So the uncertainties introduced by the paramedics do not affect the performance of the of any of the triage algorithms under evaluation. So in this sense, they are very well defined because they are very robust. Of course, we tried to push the algorithm to the limits. And then we created, and it's not shown in the table, the stupid paramedic. The stupid paramedic is a paramedic that his uncertainties for respiratory rate, overall pulse, and GCS are these ones that you are seeing here multiplied by a factor of 10. Okay? It's essentially a total incapable person. And then when we go into this, when we plotted the results, all the points fell within the diagonal. So if you do things very, very, very badly, then you are incapable of deciding anything, and that shows that everything is working as expected. The comparison with Jerome and Gutsch. Jerome worked on critical victims. The sensitivity he found was 0.44, our 0.41, the specificity 84.83. So fully compatible results. In the case of Gutsch, he gave the results grouped for all victims, sensitivity 0.88 with an uncertainty of 0.11, which is compatible with 0.77, and the same occurs for the specificity, also compatible. What happens with the blue card? We established the following criteria. Remember, the blue card, the one that is given to those that we think they will not survive, although they are alive. So there is the ethically questionable decision of deciding not to give medical care to people that we know they are living. We decided a criteria of GCS value of those, for those victims that are in the red category that have a GCS of 3 and either the respiratory rate of less than 8 per minute or the heart rate greater than 150 per minute, we assign them to the blue category. Okay, we found these values through trial and error. Okay. With these values, the percentage of reclassified casualties respect to PM star, the percentage of red casualties, the percentage of reclassified casualties that were assigned to the blue category from the total number of casualties are around 0.1%, let's say on average, for the different type of accidents. So we are only reclassifying less than 1% of the victims. Okay. If we, instead of comparing with the total number of victims, we compare with the number of critical victims, we are only reclassifying around 5% of the victims, okay? The survival probability of these reclassified victims is nearly zero. Even, I mean, of course, if you don't give them medical care, it's essentially zero. But even if they are given the medical care typically administered in a mass casualty event, another case is if they could receive exclusive, high-quality medical care. But this is not what you have in a mass casualty event. If they receive this type of medical care, even in that situation, their survival probability is zero or nearly zero. But just the reclassification of this small number of victims leads to a reduction of the red casualty mortality of 63%, which is amazing. Okay, so in front of these numbers, we can then start a discussion on the ethical aspects, but we need some quantitative value in order to argue that discussion. Why do triage algorithms fail at the end? That's the question, because we see that they are not working fine. First of all, what about the comorbidities? Well,
So there are some examples, some real case where we have this statistical take to the real data about blue.
as far as I know, not, because blue card is not applied. I do not know of any state applying the blue card.
So doesn't exist.
Well, actually, for all the mass casualty events, the only data that we have found actual data from mass casualty events is the thesis of Brunner, nothing else. So published, freely accessible data of mass casualty events. I do not know if an institution, they have their own data, but it's not published. Okay. And in the Katastrophenhilfe Bureau of Germany, this data, the data that exists is the one that published Brunner. So why do the triage algorithms fail? Well, regarding comorbidities, more comorbidities implies that you are more likely to be over-triaged, which is good for you, bad for the group. Less comorbidities is more likely that you are under-triaged, which is bad for you and good for the group. No type of injury is relevant for false positives, that is over-triage. So we did not find any type of injury that leads to a specific over-triage. However, it is more likely to get under-triage if the accident is a type of burn accident, or if the injuries are intra-abdominal or intra-thoracic. Okay. And this is essentially because the dysregulation of vital signs due to burning takes some time to set. And you can be triaged when your vital signs are still more or less in order. Okay? And this, you see that here, you see that for the burn accident, all algorithms for the critical victims are at the farthest distance from the center. Okay. Possible optimizations. Here we decided to go into a study, okay, how can we improve the existing algorithms? We proposed two possible algorithms, one called prior pulse, in which we use the actual blood pressure instead of palpable pulse. Then it would come the question, how do you measure the actual blood pressure in a situation? Okay. We are not concerned into that. Maybe we can solve, let's say, this as a practical thing. Let's see how it would, if it makes sense to do research into evaluating the actual blood pressure accurately. And then the other prior, blood pressure, which is we use the heart rate instead of the blood pressure. Here, we're coming again to the sensitivity specific 1 minus specificity plot. These are the results that you saw before with the prior algorithm. And you see how you move into that direction with the prior blood pressure or the prior pulse algorithm. So in general, let's say you go along the diagonal, but you are getting closer to 1, which is good. So, and additionally, increasing the reason that you move along the diagonal is because you improve the sensitivity by about 20%, but you reduce the specificity by also around 20%. However, in this context, the sensitivity is slightly more important than the specificity. Limitations of this method. First of all, we are using individual victims from accidents to represent mass casualty events. So the context of mass casualty events in the victim from the national trauma database that is being used to feed our simulation is lost. Okay. However, comparison with the few existing data from mass casualty events shows reasonable and good. We have to go through the indirect derivation of palpable pulse, walking, and critical bleeding. As we already discussed, the critical bleeding is not registered in the National Trauma Data Bank. We need to derive it from the medical procedures applied to the victim in order to know whether the victim had critical bleeding. Victims with different comorbidities are grouped under a single ACI value. Okay, remember, the ACI is the addition of the number of comorbidities. We cannot study individual comorbidities, essentially because if we do so, the number of victims that we will have is very, very, very much reduced per accident. Okay, we cannot. That's why we also group the age into adults, and we do not know through individual age pins and so on. The National Trauma Data Bank records only people who died during transport or in hospital. People who died in situ, they are not recorded. So in our simulation, people cannot die in situ. Okay, so our mortality is somewhat underestimated. Okay, and the NTDB does not include injuries which are incompatible with life, such as decapitation or any corporectomy. And finally, the NTDB might be biased, and actually is somewhat biased, as you saw, the pulse rate and so on is not is rounded. Some data is recorded hours after the accident. This is something that happens with all medical databases. So we have to live with it. Conclusions: existing algorithms perform at around 35% of a perfect algorithm. That's quite high, and this is in line with the intuition and somewhat rule of thumb that people in this business they have. Algorithms are weak at triaging burn casualties and those with internal injuries. And the blue card results in a significant reduction of mortality in red casualties. It is possible to identify optimizations and quantify their effects through this method. Adding the heart rate and the measurement of blood pressure to the prior algorithm increases the sensitivity, but reduces the specificity, as we already discussed. And for most mass casualty events, the sensitivity and specificity of the modified prior algorithms that we have just seen follow in the same region, but as we said, the sensitivity is slightly more important than the specificity in this context. So what I wanted to show you is, let's say, a problem from the very beginning, which is a frontier problem in medicine and in emergency medicine, and how you can apply Monte Carlo simulation to solve from a different perspective that problem and get information from databases that are normally used for other purposes. And with that, I want to thank you. This is a view of my hospital in Germany, and I am available for your questions.
Optimization of the triage procedure, should not possible to apply a stochastic approach to the beginning of the development. For example, like for artificial intelligence algorithm, for example, deep learning, or so you produce a very huge number of configuration, and after you take it in process of deep learning processing machine, and to identify what are the more critical procedure that impact on the triage activity.
Absolutely, it's a very nice idea. Yes, I mean, you can use the Monte Carlo simulation to produce training data for artificial intelligence, and then use artificial intelligence to produce proposals for optimization. Yes, I mean, we are the only guys working in this field. So there is no one else publishing in this area. This is the first work of this type. So this field is completely new and open for people to start doing research. Absolutely. This is, I mean, people interested to join this field is more than welcome. Yeah. Comments, questions? No? Everything clear? So can I give the exam now to you?
Integrals.
Some integrals? Okay, so thank you very much. Make a break.
Break 10 minutes, please, at 11:05 here, please.
Quando è questa? È sempre col giusto che c'è un database primo indice di gravità per studiare la distribuzione e così via. Però poi genera il dato proprio in accordo con quella distribuzione, non rispetto alla distribuzione uniforme.
No, la distribuzione lo generiamo rispetto a quella distribuzione.
Ah, è distribuito.
No, soltanto che il computer, quello che genera, sono numeri distribuiti tra 0 e 1 in maniera uniforme. Devi convertire questa distribuzione.
No,
altrimenti quello sarebbe un disastro.
Non capivo, pensavo che fosse poi il risultato dei dati poi facevate dei dati
Viene generato accordo con la distribuzione che abbiamo
cioè, avevo giusto la curiosità perché
No, hai fatto così.
grazie.
Sì, mi dica.
Voi fate, per quanto riguarda il tirage, operate con la Windows?
Sì, in un certo modo sì. diciamo, non cooperiamo, ma sappiamo quello che fanno loro. Il lavoro con il direttore del centro per la biologia della Bundeswehr. Sì.
Coño, te iba a enseñar dónde vivo yo. No, 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 no. Ahora déjame que me centre yo en lo
En la
mío.
foto que te iba a enseñar dónde
La
eres.
foto, la foto, le di la foto.
Sale mi casa, coño.
Encima te la en casa. Es increíble.
¿Sabes cuánto pago al mes?
100.
150. Con agua, luz, todo.
No fotis.
Sí, sí. Coño, pues ¿por qué no me quiero ir? Y me limpian todo, o sea, una vez a la semana.
¿ya?
Sí, sí, sábanas limpias, todo.
Bueno.
No soltarlo.
Encima te pagan.
Y decía, ay, pagan. Bien.
Ya, lo sé ya.
Io usavo il Monte Carlo per simulazioni dinamica molecolare.
Ah, bello. Cosa...
In realtà io usavo prima molecular dynamics,
Ok.
c'era il mio prof di Bologna, Zanner, lui ha perso anche è un sistema potentissimo.
Sì, io li usavo, ho iniziato Carlo quantico, quanto interesse Carlo di questo tipo, dopo sono passato a fare sport di radiazione
Nei materiali.
nei materiali. Sì. Nella specie no,
Cioè, quello che è bello che si riesce ad analizzare il dato, avere anche un giusto spinta predittiva per fare, o addirittura quando ecco, arriva a piede da grande, non abbiamo statistiche. Si classificano altriaci in maniera che crea
sì,
sul momento.
sì, sì.
No? Quindi sul momento devono essere le priorità in base a quello che sta succedendo, l'Italia in base alla seconda cosa, eccetera. Un sollevo in cui io sto prendendo i risultati si sta facendo, quindi avere un sistema in maniera riesce ad autodicalibrare sicuramente il tirarsi in maniera totalmente, come dire, autonoma.
Sì.
Un po' pensare
Sì,
assolutamente, perché in specifico, cioè in base al tipo di incidente che succede, perché c'è stato un attacco
sì,
e quindi lì si crea una sorta di statistica specifica per quello.
questo quello dicevo, no? Non c'è nessuno che si può lavorare di questo è un campo assolutamente. Quindi tutto ciò si può, anche questo che avevo accennato di usare l'intelligenza artificiale, quello anche una possibilità. Ma questo appena pubblicato, non so se dopo ci sarà gente che abbia un interesse. Vedo che c'è un campo in cui la gente non ha molto forte conoscenza e quindi quasi tutti gli articoli sono molto fenomenologici, quindi è difficile. Quello, diciamo, quello che abbiamo visto noi è che questo assolutamente si muove, nel senso che possiamo non solo dare dei risultati quantitativi, ma anche di capire quello che, perché non è andato bene, perché sì. Quello che faremo adesso sarà mettere anche il programma a disposizione di tutti, che chiunque voglia sono schierato in modo del genere, possono usarlo, scaricarlo, verificarlo. Ma tuttavia io credo che non ci sono. No? Tipicamente la gente in questo campo è più dal lato medico e no, noi non abbiamo potuto fare, cioè, il mio studente lui è medico e io sono fisico, quindi lui ha imparato anche a fare tutta la parte di programmazione, di capire il Monte Carlo e quindi diciamo, ma se uno non ha la conoscenza sia dalla parte medica e la parte fisica, matematica, sì. Quindi diciamo, queste simbiosi non accadono spesso.
Lo chiamava il metodo della scimmia in Monte Carlo.
Eh sì, è quello, mettere tutte le scimmie lì a scrivere. No.
Bene, grazie.
Presentazione tiene que haber puesto la primera trampa de los Black Briefs de la Fuerza Nacional. Una foto espectacular. Así dos cazaminas cruzándose y tal, y con uno va así, o sea, uno va así y el otro viene así, entonces, y el de aquí le pillas la bomba con la bandera de España ondeando sobre el que viene en contra. Es un fotón. Luego intentaron cambiar la foto y yo decía, es una mierda, la buena es, pues que ya voy muchos años con la mía, pero si es buenas, buenas. Está bien currada la foto.
Molto bene, molto bene. Ah, che mi presento. Il gatto non serve, no?
Sí, digamos que viene siendo gente como...
Pero hay algo que estaban recogiendo.
A ver, yo estoy acostumbrado a la atención al ser altísimo. Vamos a ver, así como la mitad estaba, la otra mitad estaba.
Andiamo? Sì. Vamos. Vamos.
Sì, sì, sì.
Porque tiene mucha gente que está constantemente. Ahora te escribes aquí de fondo. Que no estaba yo.
Sí, porque tú ahí, aquí, es un poco de lado.
Poi viaje.
Estás biased.
Están en el pasillo.
Al bar.
Se han ido al bar.
Desde 5 minutos que decían, 5 minutos de contención.
Mira, mira.
Las 10 empezamos.
Yo he terminado 2 o 3 minutos antes de la hora.
Más tiempo.
Mira, sí.
Pues he dicho 10 minutos.
Ahí has cargado. Pues he dicho 10, yo te he dicho 5, que de náuseas. No digas 10, no dices 10, son 15 o 20. Yes.
No, but
Hay un montón que están fuera. Sí, sí, oye.
Well, I think that we are going to start with this small audience. Grazie mille. Problem is that we have a limited time, and then if we don't increase the training, we are going to have problems to cover all the contents. Wallace? Grazie. First of all, I am Carlos Ardanaz. I'm the director of the Civil Defense School. This school belongs to the Spanish Army. However, it's a center of reference for all the remaining services in the Armed Forces. We are working for the Navy and Air Force as well. So I am going to deliver 4 presentations. The first one is about the Spanish civilian defense capabilities. And the other you have there in the agenda, so I think that we are going to explain later. This is the agenda for this first meeting, first presentation. I'm going to talk about both capabilities in the military field and in the civilian field in order to complete all the possibilities in our nation. And I'm going to touch some points about research development here in Spain and multinational cooperation that I think that is very significant in civilian defense. Well, this is the first slide about the squares and names and so on. It's very boring. We have seen here the Army, Navy, Air Force, the Ministry of Defense, and the technological laboratories and so on. I prefer this kind of slides with pillars. This is the pillars for the military civilian defense capabilities. And we have a pillar devoted to the research, development, and innovation, posted inside within the Ministry of Defense. Concerning education, we have in Spain, we have our school close to Madrid, delivering education for civilian responders and military specialists, and some courses for the contamination and the software civilian defense analysis. Concerning analysis, we have 2 laboratories of reference in Spain. The first one, Marañosa, is devoted to environmental samples, and the other one is for biological samples, biomedical samples, called ITOSDEF. And lastly, we have a factory focused on development and production of antidotes and medicines and drugs, called Semil Project, Madrid as well.
Concerning doctrine and education, this is the school that I am running now, just now, with the different courses that I have mentioned before. This course, for instance, is for specialist level in NATO standard, for captains and for NCOs. This course is for civilian responders and emergency medical services and so on. Maybe whoever with enough interest working on the public administration is able to participate in this course. This course is open for foreigners, but we are delivering this course in Spanish, not in English. For that reason, we are receiving pupils from South America or even Brazil and so on. And we are supporting many schools and universities across Spain. This is the laboratory of reference, the south of Madrid. They have a designated laboratory for the OPCW in order to have an ambiguous identification on environmental samples in case of employment of weapons of mass destruction with chemical agents. And this has the other centers integrated in the medical command. For instance, this is the Central Defense Hospital in Madrid with a specific floor devoted to high infection diseases. Many of the doctors and nurses here are attending my courses in the school in order to improve the level performing this kind of activities, mainly in the protection field. And this is the factory for orphan medicines. Mainly all of them are civilian antidotes. Okay, concerning the force. The unit of reference in the Spanish Army is a regiment. Like in Italy, the regiment, the 7th, Cremona. And we have, moreover, one NBC company per brigade, per combat brigade. Navy is more focused on protection of vessels and Navy bases, as well as Air Force is focused on protecting pilots and deployable air bases. We have a peculiarity in Spain that we have an emergency military unit. It's a brigade level unit commanded by a general with members of Army, Navy, and Air Force and trained in emergencies. This unit is called UME. These people here. And this brigade has more than 4,000 people there working for that kind of emergencies. Firefighting, floodings, even technological risk. And moreover, we have the hospital, the central hospital in Madrid. Here we can watch some capabilities in the army. The regiment is composed by a warning and reporting cell with a civilian battalion with 1 Rekikoi and 2 decontamination companies. And we have a technical battalion commanded by a lieutenant colonel with the secret team, with the more elite people. They are the most qualified officers and NCO are working there in the secret team. And the deployable civilian laboratories. It's similar in the case of the NBC coils for every brigades. They have a warning and reporting cell commanded by a captain. This captain is the advisor of the brigade commander. They have in this platoon a recce platoon with detection, identification, and monitoring capabilities, and DECO, the contamination, but only for them, not for the remaining units in the combat brigade. Moreover, we have a medical task force with 2 casualty decon stations and a specific company for EOD plus CVM. Moreover, we have in Valencia City another battalion, another support battalion in the NATO Rapid Deployable Corps with a huge GoPro systems for setting up a command post with 100 tents with this capability, GoPro capability, with filters and so on. Concerning the Air Force, this is the squadron of reference for this kind of purpose, working with helicopters, planes, pilots, of course, and working on deployable air bases. They are participating in the Topic 3 exercise in NATO sphere, for instance. Concerning the Navy, as you know, there are in every vessel, in every Navy vessel, there is a system called Citadel in order to protect the crew, and with decon capabilities in order to allow the pass between outside and inside the vessel. Moreover, they have a brigade-sized unit called Marines with a civilian platoon, civilian and E-platoon. They are UD and civilian. And they have this school for onboard safety, firefighting, and civilian. They have a specific naval civilian defense course for this kind of goals, citadel systems, and the firefighting and civilian. This is the military emergency unit deployed across peninsula. Here you can see that they have 5 battalions across Spain, and there in Madrid, we have the main unit with a regiment, and inside, within this regiment, we have this battalion level unit focused on this kind of technical and environmental risk, that's to say more or less civilian defense. They have this kind of units, RECI, deployable chemical and medical laboratory, chemical firefighting, and they are working with contaminated waters. You can see here some of the technical instruments that they are using there. They were working on the crisis of the Volcano La Palma in Canary Island, working closely with the police and Carabinieri and Spanish Carabinieri, Guardia Civil, in order to detect and identify chemicals and look for threshold. With the laboratory and with some decon capabilities. They are working now in a European project called Rescue in order to upgrading their capabilities. They have received more than 8 million euros. And once we get the operational capability, this new capability is going to be offered to European Union in case of crisis across Europe. So in the end, this is our deployment in the peninsula and Canary Island. We have 1 company here, remaining 7 companies, the regiment, the civilian defense regiment, the military emergency unit, the Navy, and the Air Force. Okay, we pass to the civilian capabilities. In this case, concerning the law enforcement agencies, we have 2 police departments. One of them is the Guardia Civil. It's similar to Carabinieri. with a double dependence from MOI and MOD. It's more deployed in towns and villages, and they have a central civilian unit, a mixed unit with AOD. This acronym means AOD, and civilian capabilities, and more qualified people, up to 100 teams. All of them are protecting our nuclear power plants with physical protection in order to avoid any problem from land and from air. And the other law enforcement agency is the National Police, it's a federal police. They only depends on the MOI. It's more deployed in city and big cities. And they have a central unit in Madrid and 28 civilian teams in region capitals. All of them are civilian defense or defenders and EOD. And they are more focused on chemical and radical terrorism. Nevertheless, all of them have been working in the corona crisis, working with open sources and chemicals wherever they happen. Medical services. This distribution is more established in different administration levels. We have this kind of emergency medical services in the local level, municipalities, and in the regional level. In the national level, we don't have this kind of competence. But of course, we have a network of 112 emergency operating centers, the treatable ambulance hospital. We have, concerning civilian, some small decontamination capability in capital of regions. Meanwhile, the big two, Madrid and Barcelona, we have a good decon capability. Firefighters is different from Italy because I know that the video focus is a national capability. In our case, it's different. Firefighters belongs to the mayor, to the local administration, and for the provinces, small regions. It's difficult to coordinate all of them in our case. So they have some capabilities and qualifications concerning TICs, toxic industrial chemicals, and they are using water decontamination in case of the need. We try to attract them, but it's difficult because mainly all of them, mainly all of the firefighters are participating in a roster with alert, activity, and resting period of time. So it's difficult to attract them to perform training activities because they are working or they are resting. So this is the current problem now. Only in case that some of them decided to give up the resting period of time, they are going to participate with us in some training activity. Concerning research, this is a new civilian defense vehicle in order to perform missions supporting our combat brigade and our larger formations. The main mission will be to perform road and area reconnaissance. And for me, the best asset is that we were able to integrate all the sensors with a computer in order to receive almost all of the alarms here in the computer. We have used the software scheme from Unitech in order to get this capability. You can see here the manufacturer is Colpro. We have chemical standoff and point detection. This is the standoff Falcon 4G. We have a micro UGV. the idea of this UGV is to dispatch the robot, for instance, to go into a basement or something like that, in order to know if inside there is enough oxygen or not, in order to make decision if we need to go with an air bottle or with a filter. We have this robotic arm. This robotic arm is able to take samples, and we can save the sample here in this fridge, or we can heat the sample and then analyze with a GCMS inside the vehicle. This robotic arms is able to take the marking signals in every case, and we put the signal here in this window, and with a laser, we are going to write down in the triangle. And then we are going to throw away the signal where the area is contaminated. We have been working with helicopters because this work was forgotten. And I think that is very important because in the end, in case of a civilian disaster, I think that all of us, military and civilians, are going to work together with everything, even helicopters. For instance, we have been working with the standoff chemical detectors, Falcon 4G, on board. And in this case, we have generated an ammonia chemical cloud, and we have been able to identify it until 3,800 meters on board. So it's very good. And now we are working with
Can I ask a question?
yeah, of course.
Do you have this kind of chemical detectors also for drones, for example?
No, this chemical detector is very big. It's very big for a drone.
Which technology is based on?
It's laser, leader. It's an active laser. Yeah. So far it's very big. I think it's better to dispatch drones with small sensors, and you are able to throw away. And this kind of sensor is able to send presence and or absence of chemical ions. This concept for me is better than this kind of chemical detector. It's the same for the radiological threat. It's a good idea to dispatch drones, very simple, maybe with a tube of Jaeger-Muller, in order to know in a specific point or a specific boundary if there is contamination or not. And we want to perform radiological aerial surveys with these helicopters with a scintillator, no, a crystal semiconductor here. We have been working with a source of session 137 there. This is the table of organization for the ongoing rescue project with DECOM teams for personnel, vehicles, sensitive material, even service animals, drone unit, logistic and communication and health. Working on this area, on multinational capability, cooperation, we have been working with Belgium and Greece in order to get a network of civilian defense facilities. This is working under a memorandum of understanding signed by our Ministry of Defense. And this way, we are able to avoid all kind of bilateral activities that we need 1 year or 2 years in advance before go there to a specific civilian defense facility. Initially, Italy signed the MOU, but later on we received a letter communicating the opposite case. So nowadays in Italy, I don't know why it's not participating there with us. We performed the last steering board meeting in April, the last month in Belgium in the DLD. DLD is the National Defense Laboratory Reference in Belgium. And this month, May, some Belgian scientific staff from this laboratory have been visiting our laboratories in order to exchange experts and to know new instrumentation, new procedures, whatever, without any workload, because we have managed this exchange only with emails. It's fantastic. Other cooperation are under the umbrella of the cluster of civilian protection, led by Germany and Czech Republic, but is located this cluster in Germany. We are working with Aerocorps in Strasbourg. We are composing a group of civilian defense experts because Aerocorps has not any lead nation. So in this case, every nations are sending experts in every field in order to support them. Who are supporting the civilian defense cell that they have them? And we are participating in this meeting composed of the commandants of civilian defense schools and commanders of civilian defense commands or regiments every year. This year was in Norway, the last year was in Austria, and the following year will be in Japan. And it's all so far. Do you have any question? No? I'm going to change the presentation. If you want, you can stand up and clear your mind, please. Okay, now we are going to change absolutely the subject. And we are going to talk about response in the case of a dirty bomb or radiological dispersal device. I am not a scientific man, Professor Lorenzo, with this kind of people. So I am not able to answer technical questions, but I am able to answer about procedures and this kind of activities. Nevertheless, with my experience, I can tell you that procedures is a very subjective aspect of life, because maybe whatever procedure is able to get success, but we don't know, because we need a real case, such as the mass casualty events he was talking before. If we are not able to get accurate data, we are not going to know if the procedure is right or not. Anyway, this is the agenda for the presentation about the different areas that we are going to work within them. Phases, the initial problem of recognition, and the control of contamination or screening, and the last slide will be for consequence management. These are my objectives for this presentation. I want to give you a framework, because these procedures are for us, but it will be good for you, adapted in order to take advantage of your resources with this event, with this scenario. Know what we need to look for in terms of quality and quantity, and to know where do you need to search. And the initial problem is the recognition of this kind of incident, because the incident, the event, is going to start with an explosion. And explosions, unfortunately, are very common. You can see how them. We are not going to have this kind of explosive with this kind of sign, maybe not. But there are one or two for explosion. This explosion was in Russia against a Russian general. Another explosion in a fireworks factory, but it's only an explosion. When we are preparing our training exercises, we are very used to employ this kind of clouds with color smokes, because we want to perform a good activity, very visual, very for TV and video. But in a real case, we are not going to have this kind of cloud. And of course, our first responders are going to attend the crisis, the incident, with firefighters, ambulances, and so on. And they don't know that there is radiation. So, what are the phases in this kind of event? I prefer call them with colors, because every color is able to report you about what kind of things are happening there. And initially, the first phase will be, for me, gray. It's dominated by uncertainty. We don't know what's happening there. And our 112 center is not going to classify this emergency, this incident, as radiological. It will be the first phase. And once we know that there is radiation, we are going to go to the red phase. Some publications are talking about the crisis management. It's a good term. Crisis management. In this phase, with victims, we are going to be in a hurry, because we need to attend the victims and to extract and evacuate them from the scenario. And we need to work very quickly. And the last phase will be the phase wait for me. We are talking about consequence management. I am using this color because we need to clean the area. So gray, red, and white. But we can initially are working with a scenario without any knowledge about radiation there in the detonation point. We need to extract people there and evacuate it to hospital, and we don't know nothing about radiation. But maybe we are going to have this kind of knowledge in a specific point. Why? Because maybe in this detonation point, we are going to have this kind of signals about radiation. Maybe we are going to show some tag about radiological sources. Or maybe the terrorists are going to release a statement by social network, because they are looking for terror and create havoc on the population. I think this is the most possible option. Maybe the firefighters, they have instruments in order to detect radiation. Maybe. But we are suspecting. When we suspect this problem, the incident commander must report all responders and, of course, the 112 center. We are suspecting that there is this kind of problem, radiation there, because of whatever. The first thing that we need to to pay attention is the smoke direction. It's significant in this case, the smoke direction. And then the incident commander must have this kind of three focus, not only casualties, but civilian population and their fair responders. The problems multiply and change. But we need to confirm that there is a relation there. Initially, we have only suspects. And we need to confirm that because in case that we have this information, we need to shelter civilian population. So there is an USA document talking about the planning for the first 100 minutes, and they recommend us to employ two instruments. They may be the same model, and every instrument should take 2 readings with at least 3 or 5 times natural background radiation, or maybe 2 off-scale instruments with high readings. You remember Chernobyl? It's the same. Off-scale means that maybe you have a high radiation level. And you need to perform these measurements 15 meters away, 1 meter high. In case you confirm radiation there, in this case, 112 need to shelter citizens in a specific radio. Not before, now with confirmation. And if we have already victims inside the detonation point, we need to extract them as quick as possible because we are aiding those and those. We are not able to perform triage activities there in the detonation point because this procedure is going to jeopardize our victims. So we need to extract the last casualties from hot zone. We don't be delayed by radiation. It's the same. We need to save lives there. And once we take away the last casualties from this hot zone, we need to undress them, to disrupt the citizens, and perform initial control of contamination, mainly in these areas. This area is significant, mouth and nose, and we are going to come back here later. Hair and hands, nails, and so on. And then we need to evacuate to the hospital, if possible, or reference for radiological problems. How we can disrobe in the casualties? This is a method proposed by the University of Herzogenaurach. This university is working closely with the United States agencies in order to improve the response with chemical disasters and chemical attacks. So they have a big facility to perform activities for decontamination purposes and for checking if the procedure is right or is improvable. Concerning the non-body casualties, we need to remove the clothing, the outer clothing, to perform control of contamination. We need to search if there is some fragments embedded in their body, because they can be very dangerous for them and for us. And then we need to grab casualties with whatever thing, sheets or towels, or what do you have? So concerning the shelter, initially we are not going to know where radiation is, or how far away is radiation. But we need to shelter people. So the initial advice is to shelter people 500 meters all directions from the detonation point, 500 meters, and establish an initial hot zone initially with 250 meters all directions. So we have here this hot zone and the sheltering zone. We need to warn hospitals, open an incident data map, and recommend personal protection equipment for everybody on the scene. Moreover, remember that we need to name a public communication officer because terrorists are thinking about generate havoc within our population. And we need to submit public messages in order to report our population. We need to name the consequence management officer from the very beginning, because this way we are going to have a smooth transition to this phase, and warn the environmental, water officials, housing officials in our city, and so on. Identifier, CRC. CRC means the Community Reception Center, because maybe we are going to evacuate people from this area to this kind of center, and we need to identify them. But only maybe, some possibility. But nevertheless, we are in a terrorist incident, and we need to respect this area, 20 meters, in order to avoid that any evidence get lost. This is the idea. So no first responders must get into this area across 20 meters in the detonation point. It's not necessary to perform this kind of measures because the police is going to perform this kind of survey there in this area. And we need to avoid moving ballistic fragments, only marking them. What about areas? When I was looking for this kind of publications, was hard for me to find units for those rates, because there are many agencies and many organizations working on biological protection, and they are very focused on protecting people, citizens, first responders, and our environment. But there are very few publications working on those rates. Those rates are more focused on marking areas. And you need, as first responders, marking areas in order to perform some kind of activities there. And this is the problem. I found this document from the International Atomic Energy Agency explaining us those rates. More than 100 millisievert per hour, with this definition, more or less, and 0.1 millisievert per hour for the hot zone. At least a clear denomination for this area, hot zone. But out of hot zone, they are talking about close to background levels. For me, this definition is not clear. Okay. This is another association in the United States, but I think that is the reference for them in order to know what we can do in case of this kind of events. The National Council of Biological Protection. And they keep the initial thresholds, 100 millisievert per hour, and they call this area as dangerous radiation zone, and for me it's better. they keep this measure, this threshold, 0.1 millisievert for hot zone, clear, and they call this area cold zone below 0.1 millisievert hour. So I think it's very easy to remember that we need to look for 0.1 sievert per hour, and this is the dangerous radiation zone, and the same figure, 0.1 millisievert per hour for hot zone. Okay? There's another association there in the United States talking about these problems, but they are more complex. They are using for areas. They keep the initial threshold for this kind of zone. They keep the lowest threshold for the low radiation zone, but they have more intermediate areas, and I think it's more complex for us. Yeah.
About the classification in this area, you must perform more time during the time this verification. Let me explain. If there are the wind, for example, I have initial explosion and I have the powder all around the radioactive powder. The wind can move the radioactive material all around. And so if I perform in the first time this classification, after I have to perform again this classification to verify if this area remain constant or modifying during the time.
I'm going to talk about that afterward. Initially, you remember that you need to respect this area before you are sheltering people in this area and declare hot zone without no more complication. So it's for firefighters or maybe a local police there. Okay? So you need to establish these areas. Respect this area and think about those rates. Only thing, because later on I'm going to explain what is happening there. In Europe, tick, tick, tack, tick, tack. We don't have any publication about that, or at least I don't find it. I think that they are thinking about the International Atomic Energy Agency documentation or publication, but we don't have any specific document for this kind of problems in the European Commission. And I think that we are going to stop here. Okay? And stop for 5 minutes. Please stand up, go to corridor, take breath.
Sì, ma ciao.
Faccio focalizzare nella parte che decía.
Good morning, nice to meet you. I'm the Lieutenant Franchi, for Italian Air. In Chetri, I don't know if you know Chetri, is another barrack, and it is complementary to Chemistry because we work in a real chemical laboratory, as for example in the university. And I have a question about for the chemical warfare agents there is and because I know that we have some problems with the treatment of these chemical agents because the immune regiment have some application how to treat it in their laboratories, they can use it and so on. So we have some laboratories that are fixed in our park. We don't know how to treat it when they are they arrived in our barrack. Some package by
Reception of samples.
yeah, at the reception and the treatment after we receive it, because we can analyze it with our instruments, HMS, because we have many instruments that can allow to us to analyze it. And we are master's degree in chemistry, so we can do it without problems. But the problem is how to treat it when they arrive. For example, how I can open it with the PI, and after I open it, how can take it and use the instruments. I don't know if you understand.
I know. And you are talking in the case of unknown chemicals. The national laboratory reference, not only in Spain, in Belgium, and I was in South Korea, I was the same. They have two instruments in the reception point. And when they use them, they go for the window to the laboratory. The both instruments are an X-ray camera in order to know if inside there is an explosive or something like that.
Okay, but this is not our case, because we know that there are no explosion in because the idea is that what we receive is treated by Cremona regiment. So Cremona regiment go in the field, take some, for example, I don't know, soil, and this soil is taken to our bag. But we think that in this soil there are chemical warfare agents. So I don't know how we can treat this, for example, this contaminated soil.
But in this case, the Cremona is going to give you the samples in free containers.
Yeah, for sure. But the problem is how to, for example, how to open these containers in a safety way.
You must open the container in a cabin.
Yeah, okay. Then, and then there is the problem, for example, how to move this soil from the I don't know, glove box from to the GMS instrument for the analysis. Yeah, I don't know if there is some publications or something that explain the passages to do it in a real chemical laboratory. Because we are not able to do it, and I like this question. I have done it also to Cremona regiment and also in the school, CBRN school in Rieti, but no one can answer to it, because probably in Italy there is no publications of this type. I don't know if you can help me, because
I am not sure, but I think that we have the GCMS in a close vicinity of the cabin.
okay.
So we can get into the cabin with the sample. Try to get what is that.
So the GCMS into the glove box.
I think so.
Okay.
Anyway, you can email me and I can answer you.
Okay.
My email was there in the.
Yeah. After I see it. Yeah. Okay. So, but you don't know. You know if there are some publications or not, because
No.
Okay.
We are working on that. So I think it is very clear that there is a procedure to take the sample from the cabin to the instrument.
Yeah.
The instrument, because we have more instruments, not only the GCMS.
Yeah. Another question is, for example, how to treat the soil after the GCMS analysis. So I perform it. For example, I see that there is some chemical warfare agents in our soil. How can I treat it after analysis? So where I can put it, how I can contain it.
You need to establish specific limits of amount of soil or liquid or whatever. Because you have much enough, in this case, you're going to have this kind of problem. How you can treat the waste.
Okay.
And it's a problem for us. In Canada, have you been in Canada?
No.
Canada, there is the main exercise for this kind of things. And the laboratory there in Southfield training area is specifying specific amount or whatever. Because they wanted to work only with small quantities.
Okay. So
But this is your limit.
you're
And you
my
don't-
decision. Yeah.
Yeah, and you don't receive anything
Okay.
apart of these limits.
Okay. So with this limit, it's simple for us to treat after then. Okay.
Yeah. But email me, and I can answer you.
Okay.
Because I don't know the specific way that our technicians are taking samples from the cabin to the instruments. But for us, I'm convinced that there is a way.
Okay. Because there is a limit of our laboratory. Our glue box is not enough big to take a GCMS instrument into. Also because the GCMS instrument have some needs some outdoor collegments. I don't know if you understand. It's difficult to take an entire GCMS
No.
into.
You only have the pro.
Okay. Only the okay. Only the yeah.
Yeah, because you need maybe helium or nitrogen for the GMS. Yeah, no worry.
Yeah, another question is, for example, after I put my soil in GCMS and I have done the analysis, how I can treat the GCMS instrument that is contaminated?
For definition, the GMS is going to
To disrupt. Yeah. Okay.
split the sample. And in the end, and you can analyze the sample.
Yeah, but before the MS part, so when for example, if I use an HLPLC, there is no the disruption of the molecules.
No, the chemical is whatever you use. Because you have what's the name? An house window.
Yeah. No. Yeah.
This is the hole where the chemical
Okay.
and molecules are going to be out.
Okay.
But you don't worry about that for now.
Okay.
There is no danger with the ending results after the analysis.
Okay.
For sure.
Okay.
But I don't know how they are taking the sample from the cabin to these places. No, email me. Don't worry.
Perfect. Thank you very much. Thank you.
Guys.
Come on. Yeah. Well, come on, andiamo. The other we start, the other we are going to finish, and we are going to have the lunch. If you want, if you want. Lunch is overrated. Nice. Interesting. For what? Okay. We are going to continue with the recommendations that we are going to provide our casualties there and our first responders attending this kind of incidents. So the first line is for whoever they are in the incident point, in the duration point, that we know that in this area there is radiation and we are not going to have any specific protective equipment for them. So the main advice will be to use dry clothing. No, nor wet clothing. Better for this kind of things, dry clothing. Whatever. T-shirt, handkerchief, or whatever. In this case, you are going to avoid that reactive particles are going to be inhaled or injected by you. And of course, once you have protected your mouth and nose, these people must be evacuated. They or with our assistance. Concerning first responders, if they are living within the first 15 minutes, they need to take SPVA, the bottle of neck with
breathable air, or at least a respirator with a filter level 3 for particles. It's not a filter for chemicals. It's only for particles. But after these first 15 minutes, we can go with a full mask, even a half mask type with level 2 filter, in order to avoid possible contamination with the case of resuspension. And now we are going to talk about what we are going to do after the initial measures that we were taking. So we know that there is radiation there, and we are going to perform a kind of reconnaissance in a near field in order to know where exactly the contamination is. This is the goal. And for that first mission, we need to know what was the main wind direction in order to look for the most contaminated area. We need to determine what is this direction. And in an urban environment, this search is very difficult, because maybe wind here is the direction, there is the opposite hand, and in the second level, whatever, It's very difficult. For that reason, in the initial slide, we were talking about what is the smoke direction in this moment, after detonation. This is a big thing. But we can imagine that we know that the smoke direction was there. And in this case, we need to expand the shelter-in-place zone to 2,000 meters to protect the public, that maybe they are going to be very concerned about contamination there in their neighborhood. 2,000 meters is a measure in order to provide confidence for population. If this area is very huge, maybe too much. And we can know later that it's very exaggerated, but we can provide confidence for population. And now we are going to look for what? Gamma, alpha, and beta radiation. And we are going to establish the hot zone, and we are going to mark the hot zone with the levels that before we can see from the International Atomic Energy Agency and the National Council on Biological Protection. 0.1 millisievert. Concerning beta, they provide us this kind of levels for beta and this kind of level for alpha. We can turn or convert this integration per minute to CPM or CPS if we want. And this is the same for this kind of surface contamination. They are equivalent. And we need to locate non-uniform high radiation areas. And we need to establish the mapping with these areas, the hot zone, and if we find beta and alpha. This way, in the end, we are going to mark the hot zone, the actual hot zone. Later on, in the response, we are going to have the support from second responders, maybe from specialized firefighters, maybe the military, who knows? It's the same, second responders. And in this case, we need to go into more specified thresholds for contamination. We are going to look for 100 millisievert per hour, that, if you remember, this threshold belongs to the dangerous radiation zone. We need to know if this level is there or no? It is very possible that we don't find this level because this level is very high for a dirty bomb. For a dirty bomb. Okay? But we need to check if there is or no. So we are going to start at 100 meters from the detonation point, and we are going to go into until 20 meters from the detonation point, because this area is only for the law enforcement agencies. Okay? In case of we learn that there is this level, we stop and mark. Enough. Stop and mark. If we have alpha contamination, this level is going to define a new hot zone. If in this area there is no alpha, we are not going to use more alpha probes. If we maybe find beta contamination, for instance, strontium 90, it's a beta pure source. In this case, we continue with the same level. And we will continue with this kind of beta probes. In this area, we need the high rate meters. Low beta, low beta, not low as well, but mainly high rate meters. And we are going to define if inside there is a dangerous radiation zone and what is the actual direction of highest radioactivity. Maybe in the detonation time, there is no wine. In this case, all the reason is there. Here located, or around detonation point. But in case of wind, the particles are going to fly in a specific direction. In the second phase, we need to know what was the maximum range from contamination. So we'll go to 1 kilometer and then we perform survey in intervals of 50 meters in order to detect if there is a hot zone activity there. This is the idea. If we find that it's difficult for a dirty bomb, in this case, we are going to expand for another kilometer and then we are going to come back. But it's difficult to find here particles from a detonation here so far away. We can use alpha and beta probes in case of alpha beta before in this area. And it's all for this case. When we know what is the maximum range, we need to perform survey meters in this area in order to know the boundaries between hot zone and cold zone with this threshold. And in this area, we can use low dose rate meters. We are mapping the contaminated area. This is a table that I find in an old publication from 2010. It's a comparative study with different sources for nuclear accidents, these numbers, for explosion model. Using this hotspot code is an old code. And in the case of explosion, they are thinking about TNT 500 grams of this kind of explosive. And they are using cobalt, cesium, and iridium. And you can see the most dangerous source will be cobalt, but you can check that on ground, this level is only up to 200 meters. 200 meters. Maybe this result is not very accurate, but it's going to provide you an order of magnitude. We are thinking or talking about hundreds of meters for hot zone. Okay, Here you can see that on the air in bloom, there are more distance. But for me, the important thing is that with this level. And later on, with our second responders, or maybe with other firefighters or whatever, whoever, we need to perform activities outside the contaminated area in order to provide confidence to local population, talking them that in this area there is no contamination. We can think that these activities are useless, but we need to provide confidence because there will be more fake news about this event for sure. And moreover, the terrorists are going to look for this kind of problems for us.
Sorry. For this vision, you use ATP 45 or no?
No.
Yeah.
They are using, no, you are talking about that? Or no, it's a scientific publication there.
Okay.
And they are not using the ATP 45. The important point, communication with the public. We need to establish previously to the event a public message prepared for this kind of incidents. At least 3 of them. The activity is confirmed, and you need to submit protection measures for population. The second message will be to shelter in home, and you need to explain why. And maybe another basic will be, if you are very nervous or you are thinking about you are contaminated, take a shower. It's very relaxing. Yeah, people will be very concerned. Take a shower. It's very good. Water is not contaminated. Okay? But nevertheless, we need an official devoted to this kind of task, and we need to establish the messages. Control of contamination or screening of contaminating people. I want to repeat that it's significant that we remove the standard clothing of people. We can use wet wipes to clean exposed skin, for hands, for the face, or whatever. In case of we don't take any contamination around mouth and nose, we can assume that there is no significant internal dose. Significant. It's a good point. So you need to take a precise lecture or reading here close to the mouth and nose. Concerning where we need to establish or to locate the community reception centers, they must be placed in areas without contamination. We can talk about twice background radiation level, okay? Or at least this level, this is a 0.5 microsievert per hour. Nevertheless, yesterday I was flying to Rome, and there on the air with my personal dosimeter, I was taking readings of 1.5 microsievert per hour. So whatever you want is a good reading for you. It's not dangerous. Sorry, we need to be very empathic with the population because we are going to be very nervous. We are working with contamination, and they are going to be very nervous as well. So please don't cry them, don't put them more nervous than they are. Use kindness and politeness in order to give them instructions, in order to remove clothing, use wet wipes or whatever. It's important. Dry decon, of course, is the best, but maybe somebody want to use water decon. In the case of a dirty bomb, we can use this kind of decontamination techniques. The level of contamination is going to be very low. And please don't waste efforts in control of this kind of contaminated water. In this phase, we don't devote any effort on the contaminated vehicles. We can give up. And remember that in the initial phase of the event, there were casualties evacuated to hospitals before recognition. So maybe inside ambulances and inside the hospitals are going to be contamination. So we need to dispatch some responders to go there and to check if there is contamination or not. Beyond, this is a phase that nobody's working on that because everybody's working on the crisis management and nobody is providing resources to improve capabilities on consequence management because this training is very long. For the initial phase, for the crisis management, the red phase, we can finish in maybe 30 minutes, no longer, because we are going to evacuate all of them in 30 minutes, as much as you can imagine. But this phase is going to require a long time, with monitoring across time, a long time of all areas and underground these areas. You need to decontaminate surfaces, tubes, corridors, and whatever. Vehicles, I think that we can control of them and look for this kind of contaminants, radioactive contaminants. We need to designate repository areas. It's similar to the case of Brazil, Guyana. They designated these areas in order to put all the radioactive remains in specific areas, making a difference between the different level of activity. This area for high level of activity, this area for medium, this area for low level of activity. And we need to monitor these areas at a long time. I recommend authorities to use this kind of software, GammaPix, because it's very useful for downloading in mobile phones and maybe in surveillance cameras, because this software is going to use the LCD camera of our mobile phones or of this kind of surveillance cameras in order to detect if some photon is crossing the screen. And we are going to know if there is contamination there or not. Maybe it will be not necessary because nobody is going to find anything. But this way, we are going to provide confidence to the population there in this city. We need to start with the medical treatments for casualties, knowing what was the specific isotope there in the incident area. For that reason, it's very significant that in the initial phase, we need to identify the isotope. Because according to this identification, we are going to perform a specific medical treatment. And of course, I think that we are going to start the control of internal contamination with our body counters. And we have few number of body counters. So we are going to require a long time in order to check pupil and population and to confirm possibly that there is no contamination there. It's the same than in Fukushima incident. Fukushima disaster, many people were in the body counters in order to confirm that there is no internal contamination. And it's all. These were my objectives for you. I hope and I expect that you get it. And this way we can improve your capabilities in your specific areas of responsibility. This is our references for this presentation. And if you have more questions, we can finish here, go to lunch, or answer your questions. away. But respect timing and 2 o'clock here, no later. Question? 2 o'clock here, please, no later.
Okay.
Io vado a
Only
Qualunque arrivare.
has the contamination by water.
No, andiamo in mezzo,
How
dai.
did you decide to
Sicuro.
Io vado alle verdure. No, ieri sera
with the dyeing instruments and